All right, we're going to transition, right? We've been talking about conduction. The entire class so far has been conduction. We are now moving into, I'd say, like the second unit of, this unit's kind of the wrong word, but kind of the second stage of the class. There's really, I'd say, three stages. There's the conduction part, there's convection, which is what we're doing now, and then there's other stuff, we'll say, like radiation, heat exchangers, that kind of thing. So we're going to be talking for, let's say, the next quarter or so of the class about convection. What we're going to do is, first we'll do recap. So if you've had heat transfer class before, a lot of this stuff will look familiar, but maybe give a new perspective on what you've been talking about previously. But then we'll get into stuff that maybe you haven't done before. We're going to go through and derive the Navier-Stokes equations for boundary layers. We're going to do some things around simplifications that you can use to come up with analytical models of convection. So far, we've really just said, if you have convection, you describe that in some way with a heat transfer coefficient, and I give you that value. Right? Now what we're going to do is use the concepts that we have available to us to be able to predict those values for different situations. So we'll go through, like a few different ways of dealing with this. We will talk about both laminar and turbulent flows. We're going to start with laminar because I think conceptually that's the best place to start, but we will get to turbulent models later on. So, okay, let's start with some concepts around boundary layers in external flow. External flow is, again, it's like the simplest place to start. We'll get to internal flow. But first, let's understand what we mean by boundary layer. What do we mean by external flow? So let's start with a sketch of what a boundary layer looks like. So boundary layer behavior might look something like the following, where if you have some plate where there's coordinates here, let's make our coordinates. So this is the y coordinate, and oops, this is the x coordinate. If I wanted to plot the velocity profile of fluid that's moving over this plate as a function of position y at some location x, what would that look like? Well, that would look like the following. I would have, coming in to the plate, I'm going to have some uniform velocity distribution. Right, that uniform velocity distribution is because the free stream is sort of moving. There's nothing interacting with it. It's all just moving as a bulk flow. Eventually, it starts interacting with this surface. At this very leading edge, it starts interacting. And it's going to start deforming the shape of this velocity profile. So very near to the wall, there's something called a no-slip condition, where the velocity at that location has to be 0. Right? There's no slip. There's no movement between the fluid and that surface. That, by the way, is actually an approximation, but it's usually pretty accurate. So far out, you'd have your normal velocity out here, your free stream velocity. But as you get closer and closer to the plate, the velocity drops. Right? So you'd have something that looks like, let's say, like this, right? So your velocity profile is going to do something like this. So this would be, we would call this u as a function of y, right? So we're saying the velocity profile u is a function of y at some position x. So this is the velocity profile, but what do we mean by a boundary layer? Well, a boundary layer, as it applies to this momentum situation, is any part of the velocity profile that's affected by the presence of this plate. So this would be, in this case, I guess we kind of drew it where maybe this location is essentially the cutoff of where you're going from free stream velocity to affected velocity. So we would call this boundary layer thickness, delta sub m. And that would be the distance between the wall and the affected position. Delta sub m comes from the fact that this is momentum. Right, so it's a momentum boundary layer. By the way, I'll consistently, hopefully, write BL instead of the full words for boundary layer. So the momentum boundary layer is the velocity profile that's affected. If you really look at this equation, or you look at the reality of this, there's not like a clear single point where there's no affected position and then it is affected. So normally what they'll say is you can use a cutoff of something like approximately 99% of the free stream velocity. So if I know my free stream velocity over here, let's call this U infinity. If I know that free stream velocity, I'm going to look at which point is my velocity 99% of that value, and that's a good cutoff. So it's an approximation, right? If you make it 100%, you'd go way out past the point where there's sort of a meaningful impact. So that's the boundary layer. If we plot out the temperature part of this, let's draw another sketch here. So I'm going to make this a little bit bigger. So what I'm going to do is make my x-coordinate here, and I'm going to plot the boundary layer as it's growing. So the thermal boundary layer, right when it hits the edge of this plate, right, so you have this free stream coming in here. This is at let's say T infinity. The thermal boundary layer develops much the same way. So let's say we're at T infinity and this surface is at some other temperature. We could call that T sub S. That's our surface temperature. So as that fluid that's at a single temperature starts moving across this plate, what's going to happen? You're going to start getting heat conducting away from this plate into the fluid. And that wave, or that thermal wave sort of propagates as you move along in this direction. That wave has time to grow. Just as the same effect as here, where you start seeing there's this disturbance and that thing has time to grow. So if we looked at the thickness of the boundary layer as a function of position x, it might look something like this. I'll draw it in blue. So it's going to look something like this, where you have a kind of faster initial growth, and then as you go further and further out, it continues to grow, right? It's always going to continue to grow, but it slows down. The rate of growth will slow down. So this would be our thermal boundary layer. If I pick some location, let's say I'm going to pick a location here. That's really hard to see. Do this instead. So I'm going to pick a location here. My boundary layer thickness is, I guess, obviously this thickness here, delta sub T. And that is changing as a function of position. If I plot the temperature, so we did the velocity profile. If I plot the temperature profile as a function of y position, where this is my y position, it's going to look something like the following. So I would have, let's see what color. I'm going to try using red. So let's say, how to draw this? So let's say I have an axis here that is drawing my, do it like this. Right, so this direction is temperature. So I'm kind of flipping a plot on its side, and then you'll kind of see how it looks. Let's say this is this point here is T sub S. So I'm going to plot the temperature as a function of y, imposing this sort of flipped temperature axes. Oops. And that would look something like this, right? You have this kind of steep approach, and then right at the edge of the boundary layer, you become the free stream temperature. Does that kind of make sense what I'm drawing there? You have temperature here, so this is at T sub S, it's right at the surface, and then the temperature is going to quickly ramp down and sort of slowly approach this boundary layer, the boundary layer position where it becomes the free stream temperature. As we move out in space again, so let's pick another point out here, you kind of get the same thing. You're going to again have your T sub S, and it's going to do sort of a similar thing where it sort of ramps down. But you see that now as you go further out, this gradient, dt, dy, becomes smaller. So think about what that means for a second, right? I'm saying here, this gradient dt, dy is smaller than the gradient dt, dy here. So what does that say about the heat transfer rate as I go out in position x? Smaller, thank you. Right? You're forcing the conduction, the rate of conduction in this direction to match the rate of convection here, but it's still, right, you still have to match across the surface the heat transfer, the energy is conserved. So you're going to have less heat transfer as you go further out and your boundary layer grows. And it's just a matter of looking at the slopes of temperature as a function of position. Okay? So this, I mean, I think this kind of gives you the idea. We're saying t, just by the way, t sub s is greater than t infinity. But this gives you the idea of what's happening in a convection problem. And I think a couple important things to point out. So first of all, we're talking about laminar flow here. Right? Laminar flow is a flow condition where there's no velocity component in the y direction. So maybe it's important to say that. So there, u sub x is not equal to 0. U sub y is equal to 0 for this case, for laminar flow. And if you look at like the word laminar, go to the, I don't know, it's Latin or Greek or whatever it is, it actually means like sheets, right? Laminations. So you have these basically sheets of fluid that are just sliding over each other. There's no velocity component in the transverse direction. So because it's laminar flow, it behaves in this kind of consistent way. So this is our like conceptual stuff that we need to know for laminar flow. I guess what else can I say about this? For this problem, for the boundary layer, for thermal boundary layer, we would say that where t minus t infinity over, t minus ts over t infinity minus ts, right, where this is less than 0.99, that's our criteria. I guess it would be absolute value, right, because it would be flipped for this case, but where there's a disturbance of less than 1% of this sort of normalized temperature, that's where your boundary layer exists. Okay. So just conceptual stuff so far. Any questions on this? Yeah.
Is the boundary layer thickness a function of position in x? Or is the thickness constant throughout the domain? Or
it's going to change, right? And that's what we're showing here with this blue line. So this is sort of this threshold, that's 99% threshold, where right at the leading edge, the thickness is actually 0. So it's just, you can just imagine the fluid is coming in, hitting this, it's like flow over a table or something, right? It's just hitting the table. So the fluid has, all coming in at free stream, it has had no time for that, any momentum or thermal effects to develop. So you get this really steep, infinitely steep gradient right here. And then as this thing grows, or as you go along the table or along the flat plate, the amount of fluid that's affected by the presence of that thing just sort of grows. Right?
okay, but then it tapers off eventually and stays.
No, it will continue to grow indefinitely. So we heard the question. So will this, as I've drawn it, it looks like it's going to taper off and become constant. It's going to continue to grow in this direction indefinitely. Now, at some point, you're going to get such, we'll talk about this more, but at some point, you're going to get such a shallow gradient or a small gradient of velocity with respect to y that the shear stress becomes really small and it becomes unstable and you get turbulent flow. So eventually, the flow will transition to turbulent. But if it was prevented from doing that, that boundary layer would continue to grow indefinitely.